Okay, YouTube, this is the first in a couple of videos that I'm making on solving logarithmic equations. I think I'm just going to run through a few examples just to kind of show how some basic ones are solved and some very, very common logarithmic equations, what they look like. So we're going to be borrowing from a couple of properties. Recall that we have a one-to-one property when it comes to logarithms. That is, if we have two logs, let's say they both have base a, so log base a of x was, say it were to be equal to log base a of y, then this would imply that their arguments in there would have to be the same thing. That would be true if and only if x was equal to y. And the other property we're going to be using is this property that basically says this. If we had base a to the power of log with the same base, so base a of x, the base a and the log base a would cancel, and you would be left with just the argument up there, which is x. Okay, so which is convenient because that means we can exponentiate in order to cancel out a logarithmic thing, which is what we're dealing with, logarithmic things. So let's go ahead and take a look at letter A here. ln of x is equal to 2/3. Now the first thing I want to mention is this. Recall that ln of x is really a fancy way of just saying, or an elegant way really, of saying log base e of x is equal to 2/3. So what we want to do here is this. We want to undo a logarithmic thing by using its inverse, which is this second property up here. So in order to undo a logarithmic thing, what we're going to do is we're going to what we call exponentiate both sides. So I'm actually going to take a moment to write this out here. Exponentiate both sides. I have to concentrate because it's kind of hard to write with this thing. So exponentiate both sides using the base that we want in order to cancel out the base of our log. So what we're going to do is we're going to say e to the power of everything on the left would be the same thing as e to the power of everything on the right. And this is kind of a twisted form of the one-to-one property, because if e to the power of this was equal to e to the power of this, then the stuff in blue would be equal to begin with, which is our basic premise. So what I know is this. E to the power of ln of x, that should cancel out, and we're left with just x. And on the right-hand side here, we have just e to the 2/3. So the convenient thing about this is our calculators, if you have a calculator, has a button on this for that. So we say x equals e to the 2/3 power. We say e to the power of 2 divided by 3 in parenthesis. Make sure you get that in there. We say, okay, so this comes out to be approximately 1.948. So we say x is approximately 1.948. which is easily checkable in the original equation. If we were to take ln of 1.948, we'd see we'd get roughly 2/3, which is about 0.666. So ln of 1.948, ln of 1.948, there's our roughly 2/3 right there. Okay, so it checks out. Letter B up here on the top right, we say log base 4 of 3x plus 2 is equal to log base 4 of 6 minus x. The nice thing about this is we have two logs that are set equal to one another, and you'll notice here that they have the same bases. So as per the one-to-one property, we can go ahead and say, well, then their arguments must also be equal. So it is the case that 3x plus 2 must be the same thing as 6 minus x, and we can start isolating things here. So if we brought, say, we kick this x back over to this side over here. We say, okay, so then we have 4x's plus 2 constants is equal to 6. That is, 4x equals 6 minus 2 is 4, and this would necessarily imply that x equals 1. And this can be checked easily up here. If we put it back into our original expression, we say 3 times 1 would be 3 plus 2, so we get 5 inside this log. And we say if we plugged in a 1 right here for this x, we'd get 6 minus 1 is 5. So log base 4 of 5 equals log base 4 of 5. Groovy. It all works out. So now example number C, letter C down here. This is a common example, so it does actually borrow from a property of logarithms, which basically says this. If you were to, say, take a log base a for the sake of convenience here of a quotient, so u over v, we could rewrite this as log base a of our numerator minus log base a, same base, of our denominator, okay? What we'd like to do is actually take this difference of two logs and rewrite it back as a quotient. So you'll notice here that we're taking the difference of two logs, log base 3 of this minus log base 3 of this, where this is like our u here and this is like our v. So now we can recondense this, okay? So condensing is actually the term we use. We say log base 3 of the quotient of these two things, where the first thing we had in our difference was 5x plus 13. and this would be over 6. So basically working backwards, and we say this is the same thing as what we had on the right here, was log base 3 of 3x. And so now we have two logs that have the same basis and are equal. It would be fair to say at this point then, therefore, 5x plus 13 all over 6 is the same thing as 3x. And then we can go ahead and go about solving this. Sorry, that bouncing thing was getting in my way there. So going about solving this bad boy, we could multiply both sides by 6. That would get a little bit of substance out of the way. So we'd say, okay, so these 6's cancel, and we have 5x plus 13 is equal to 18x's. And then we could bring all, what if we bring this 5x over here? We have 13 equals, hey, what do you know, 13x. So therefore x is 1, and we would want to check this in the original expression. If we plugged a 1 back up here, we'd say, well, we had log base 3 of, let's put it in this second expression. If we put in 1, we say 5 plus, 5 times 1 plus 13, so 5 plus 13 is 18 on top over 6. And then over here, if we put a 1 in, we'd get 3. So we say 18 over 6, well, that reduces down to 3. So this would have been log base 3 of 3 is equal to log base 3 of, over here we would have gotten 3, and that checks out. So a few quick examples on how to solve some logarithmic expressions.